that makes me an affiliate of probably the university for today. Yeah, so I will.
Sorry, just one thing I forgot. We are going to record this, if you agree.
Yeah, sure.
Okay. Okay. Please go ahead.
Yeah, let me tell you about maybe some new perspectives on some already medium old work together with Nguyen, Pauwels, Redondo, and Solotar. And it will be about computing the Gerstenhaber structure for an algebra with a particular emphasis on using gradings. So let me just briefly go through notation for Hochschild cohomology and start out with a bit more general remarks. In what follows, I will make some general remarks that hold for any associative algebra over a field. It's as usually considered as a bimodule over a tensor the opposite algebra. As such a bimodule, one has the bar resolution and computes the cohomology of the homomorphisms from the bar resolution to the algebra, everything considered as a bimodules. Just as a note already, the two prominent Hochschild cohomology guys are zero Hochschild cohomology, which gives the center of the algebra, and more importantly for us, the first Hochschild cohomology, which is isomorphic to derivations on A modulo inner derivations. But I'll come to this again in a moment. Now, from all these definitions based on the bar complex, everything on Hochschild cohomology is quite hard to compute, and even harder usually is the Gerstenhaber structure. The nice feature in theory is that Hochschild cohomology is a graded Lie algebra via the Gerstenhaber bracket that goes from n times m degree to the n plus m minus first degree via the commutator with respect to the circle product. The circle product works by taking one of these tensor monomials and kind of plugging in first g applied to m tensor factors and then f applied to everything else. And again, everything is very bar complex heavy, so computations get very messy very soon, even though this is a very nice structure in general. Now let me start out with the other kind of topic for today, which are the degree derivations. So as mentioned, first Hochschild cohomology consists of derivations on A, modulo inner derivations. That is, derivations are zero if they are obtained as the commutator action for some element on A. In general, the multiplication rule for derivations holds. That is, well, just the ordinary product rule. So in other words, products will be resolved with some kind of addition. And now, if soon as we have a let's say Z grading on our algebra, then we have some very special derivations, that is degree derivations. So A decomposes into its homogeneous graded components, and we can assign a degree derivation that takes each homogeneous element to its degree times the element. And this is indeed a derivation, as a short computation shows, and it's this additivity of the degree that matches the the addition in the product rule, because if we evaluate what's happening on a product, what we get is really the sum of the two degrees, and this is the same as required by the product rule. So even better the situation gets if we have some z to the k grading, because then we can easily collect k degree derivations from that, and we might lose some derivations again, because if the grading is actually some so-called inner grading coming from some commutator action with an element in the algebra, then of course one can realize it as an inner derivation, and it vanishes in first Hochschild cohomology. So this notion is very important and really at the heart of this talk. So I would like to have everyone remember that these are our main objects for the theoretical part. Now, Gerstenhaber structure is hard to compute, but the nice thing is that first Hochschild cohomology is preserved under the Gerstenhaber bracket and is a Lie algebra, and so one can consider the action of first Hochschild cohomology on all other cohomological degrees just by the commutator action with respect to the Gerstenhaber bracket. And this is a Lie algebra action. So typical goals are to describe the first Hochschild cohomology really as a Lie algebra, and then describe the Lie modules HHN of A. And as my assistant is pointing out, we want to see particular what's happening for graded algebras. So first of all, let me remark that if A is graded, we get another nice feature. That is, we get an induced grading on Hochschild cohomology. And this is because if we go through the definitions of the bar complex with all the tensor products involved, we first note that, the algebra A times A op is inheriting a grading by, just adding the degrees of two tensor factors in a monomial expression. And similarly, also, all the other components of the bar complex carry a grading, and they are graded as AE modules. The differentials preserve the degrees as they never change somehow the occurrence of these monomial factors AI. They just multiply them and add them up, but this is all homogeneous. So in other words, the bar complex resolution of A is a graded resolution, and similarly also homomorphisms can be graded by saying that the degree of a map is the difference of the degrees of the pre-image and the image. So by all of this, Hochschild cohomology obtains a grading, and so it decomposes itself into a sum, now just as a vector space, into its graded components. And it's just a bit messy now to keep track of whenever one says degree, whether one is speaking of the cohomological degree or this induced internal degree. And now thinking of this degree derivation that we introduced. This is a diagonal or diagonalizable derivation. So in other words, really everything will just decompose with respect to this derivation into eigenspaces. And it has a lifting to the bar complex given just by multiplication with degrees, because everything will just go through if you look at the definitions. And so from that, one can get quite immediately that the Gerstenhaber bracket with such a special derivation, such a degree derivation on a homogeneous representative inside some n Hochschild cohomology will be again just multiplication with the degree of f. Right? So once A has a grading, we obtain two things from that. The n Hochschild cohomology is graded, and we have this nice degree derivation, and everything is just behaving nicely with each other. So from there, even the ugly definition of the bar complex gives us already the evaluation of these degree derivations under the Gerstenhaber bracket. But of course, this is something very special, and so let me advertise again that also in what we did in our collaboration, we made heavy use of Mariano's method for the computation of Gerstenhaber brackets, because what we have seen so far was just bar complex based. And indeed, of course, one can go through this construction just for the bar complex at first, to consider just any derivation representing an element in HH1 of A, giving an explicit method how to obtain the Gerstenhaber bracket with such an element in terms of a much easier map that can be defined in particular on any projective resolution, so also nicer projective resolutions than just the bar complex. So keeping this in mind, that we can also switch to a more convenient projective resolution in case we need it. Let's summarize for the moment that what we get is our Lie algebra HH1 of A. However else it looks like, if A has a grading, then there will be as many degree derivations, maybe not linearly independent, but we don't care for the moment. But so just some degree derivations obtained from such a Z to the L grading, and this is a commutative subalgebra inside this Lie algebra HH1. So HH1 decomposes into root spaces with respect to this action, and similarly also the nth cohomological degrees decompose into eigenspaces for this action. So it's really like root spaces and weight modules, and all of this just obtained from simple gradings. So now, with all this material in our backhand, let's look at a special example. This was also our starting point in our collaboration, to look really at how can we obtain the Gerstenhaber structure for the following example. So we fix some integers uppercase n and lowercase m, and we consider the quiver with m vertices. That is this circular quiver with arrows going in both directions, and its path algebra over some field that can be more general, but just for the moment we can just speak about complex numbers to not have to fuss about the possible characteristics. And we mod out the relations that whenever we go 2 steps into the same direction, then this is 0. So AI plus 1 is 0, as well as going in the opposite direction, AI plus 1, AI. And then some cycle at the node I that is repeated n times will be equal to the cycle somehow in the other direction, right? So if we start at I, we can go n times in this cycle, and this will be equal to going n times that cycle. And in particular, so if we post-compose within any of AI or AI minus 1, then this will be 0 due to this other rule. And there are 2 interesting gradings for us. And one of them is by assigning to the arrows in the clockwise direction the degree 1, and 0 to those arrows going in the other direction. And there's another grading, obviously, by taking the clockwise arrows to be in degree 0, and all the anti-clockwise ones to be in degree minus 1. One could have chosen, of course, a different grading, but we will see later on how this grading matches up nicely with work by Snashe and Taipei, on which our considerations were based. So in this, for this algebra, we wanted to describe the Gerstenhaber structure, and in my more theoretical part, I was going exactly in the opposite direction through what we really did in our collaboration, which was that we started out by the attempt to compute anything for this algebra without having this grading in mind. But we thought that it might be a situation where we can apply Mariano's methods, and it turned out that we could, and we obtained quite a lot of results on the structure. So let me first give you the overview of what happened. So the story before we entered the scene by Snashe and Taipei was that they already computed the Hochschild cohomology of these special biserial algebras as K-algebras. So they gave a really nice minimal projective resolution. They had bases for each of the cohomological degrees, and they computed quite a lot of cup products on that basis. There was nothing known on the Gerstenhaber structure up to that point. And this was what we wanted to achieve in our work. So what we did was to compute the Gerstenhaber bracket on algebra generators. So together with Poisson identity, you can reconstruct everything in a tedious way from there. And what I want to focus on right now is more that we gave a full description of the Lie algebra HH1 and its action on all the other cohomological degrees. Yeah, so this is what I would like to discuss now. So a very lucky fact for us in the hindsight was that the projective resolution constructed by Snashe and Taipei is a graded resolution with respect to these gradings. And also these bases that they give are homogeneous. And maybe this is not such a huge coincidence, because for quiver algebra, it's of course nice to have such a grading where you just assign degrees to certain families of arrows. and if the relations are not too bad, we can hope for them, of course, to be preserved. And well, we've seen from the defining relations of the quiver that in particular this non-monomial relation here is homogeneous with respect to this assignment. So yeah, oops, I'm very sorry. I have to everything backwards now. Okay. So this makes a lot of sense, and everything that is really described under in terms of nice monomials inside our algebra has good chances of being graded. So let me go quite slowly now a little bit through the notation that was introduced by Snasher and Taipei. So first of all, this projective resolution is defined by giving some basis for the E bimodule, where E denotes the space spanned by the idempotents attached to the vertices. And then they consider elements given by linear combinations of paths that are all starting at a vertex I, and that have, in case our n that is ruling the additional cycle relation is 1, then these paths will all have length n and have precisely r steps in the anti-clockwise direction. So in other words, n minus r steps to the clockwise direction. So you can start at I, and from there you can just go maybe some steps anti-clockwise, then turn around and go clockwise again, and then go a little bit anti-clockwise again. Yeah? So it's there's some certain recursive rule how to define these elements, and it's a bit maybe too much notation for such a talk, but yeah, they give these very explicitly. And in case our cycle relation is for n greater than 1, to these paths there will be some cycles around a vertex attached as well. So this is messing a little bit with this intuition for that they consist of n arrows, and because at some points you might somehow stop at a vertex and loop around n minus 1 times. Everything here is still quite difficult computation-wise, even though it is of course much smaller already than the bar complex, but it is very still a lot of computations to do if one has to work with this complex explicitly. But they were brave, and they did, and they came up, for example, with the basis for the first Hochschild cohomology given by elements that take one of these generators for the first for n equal to 1, and they map such a guy attached at I to the arrow AI. And in this case, not so much is happening, because in fact this G0I1, well, it's a one-step move away from vertex I without any reversed arrows. So this is AI. Yeah? So this is just mapping AI to AI, and the anti-clockwise arrows are mapped to 0. They are not part of this linear combination here. And so in other words, we can identify this derivation belonging to this phi with our degree derivation for the first grading that we discussed, right? Where we assigned to each arrow in the clockwise direction the degree 1. So, well, it's just multiplication with 1. And 0 to the anti-clockwise ones that are annihilated by this phi, indeed. Similarly, one can go ahead for the anti-clockwise arrows and map the anti-clockwise generators G1 I1 to the anti-clockwise one. And as in these linear combinations that define the G are some signs included, this is why we want to have the minus sign to match up with everything that is in this Nash-Shell type pair work. So here, indeed, the clockwise arrows are mapped to 0. The anti-clockwise ones, decorated with the minus sign, are mapped to themselves. So this is corresponding to the degree derivation for the second grading that we looked at. And otherwise, there's a bunch of elements that are denoted E1JS. And also these, they look maybe at first a little bit intimidating, but let's look at them for a second. So here we have, in fact, that the basis element with that is just the arrow AJ going from J to J plus 1. This one is mapped basically to itself, but then we attach some S times the cycle around the J vertex. So this one here is really increasing the number of steps that we're doing. So sorry. And we can do so for any vertex and for any number of cycles that we take between 1 and n minus 1. If we take S to be equal to n, then this is nothing but the 0 map, because then via this exchange relation we can replace this cycle by the one along the vertex j minus 1, and then we get 2 steps in the same direction, and this is 0. So this is the basis computed by Snesher and Taipei for HH1, and we can already, it's really very lucky, right? Here we already see the gradings that we just that one is able to just define right away when just looking at the quiver. Indeed, we find 2 degree derivations, which we did not know at first. So this is already giving some spoiler on what we did, in fact. Now, for the description of the Lie algebra HH1, again, remember that there's the basis given that we just discussed. So we have the first guy that corresponds to our first degree derivation and our second degree derivation. And then we have these E1JS that attach to the arrow AJ the cycle around JS times. This basis here can be rewritten if we just take the sum of these degree derivation respective the difference of these degree derivations, and well, if we replace our basis elements by these two that we want to denote C and E0, then what we get from there is a very easy description of the Gerstenhaber bracket. And this is that the C is central, as the name suggests. So its Gerstenhaber bracket evaluated at any other element is 0. Then we have our newly defined element E0, that is the difference between the two degree derivations. And this one will indeed multiply E1JS by S, which is quite clear again if we just remember the definitions and keeping in mind that if everything is graded, then everything is very simple for these degree derivations. So this one will just check out what the degree of such an E1JS is, and if we look at it again, it did attach S times arrows to a given arrow. So if we compare the degree of the image and the pre-image, then we see from there that we get the factor S. And then what remains to be computed, but which can be done as well. I will comment on this in a while. So the Gerstenhaber bracket between two of these more complicated guys that are not coming from degree derivations, this will be that if we compute the Gerstenhaber bracket, first of all, it vanishes unless we are speaking of the same vertex here. And if we are at the same vertex and S plus R is still less or equal to n minus 1, then we will go from E1IS and E1IR to E1IS plus R with a factor of R minus 2S. And this sparked our interest because we realized here that this looks very much like truncated Virasoro algebras, and indeed what we could show was that we have an embedding of this first Hochschild cohomology as a Lie algebra into m copies of truncated Virasoro algebras plus a central component that got lost somehow in the truncation procedure and that we add artificially afterwards. And to give a reminder on the Virasoro algebra, that's a Lie algebra that has as basis a central element and elements indexed by integers. And now taking the Lie bracket between two such generators indeed reminds of what we've seen before, because we get again this factor R minus S, and the indices add up to LS plus R. And then there's an additional summand that is living in the center, but this guy here dies if we look at truncated Virasoro algebras that are merely generated by the LS with positive index, and then we mod out all those LS that have index greater to n minus 1. So this quotient here, which one can verify again, well, indeed it is a Lie algebra, and it is exactly what we found here, and we get one copy of this for each vertex, and then there's the central component that we still need to add artificially. So this was quite thrilling for us that indeed we could find the Gerstenhaber bracket in this case explicitly. And from there, we wanted to explore then the module structure for all the other cohomological degrees. First again, let's look at what Snellsche and Taillefer obtained for the description of the center of the algebra AN. And this one has a basis given in terms of, well, there's the opposite generator, the 1. And then other K basis elements include cycling n times around one vertex and taking the S power of cycling in both directions. That is, as a picture, you can imagine it like that. So either you just cycle around n times, or you take going from I to I plus 1 in the opposite way, and then from I plus 1 once along I back to I plus 1. And this is Fi, and well, you can then take the S power to obtain the evidence here. Now, as a module over the Lie algebra HH1, this one here decomposes differently for M even or M odd, and in both cases we have one-dimensional summand given by 1, and then these decompositions differ a little bit. So for M odd, we have the direct sum of again M indecomposable summands that are quite nice to describe. So this looks yeah, like well, a Virasoro module where you have you start out by Fi, and whenever you take the Gerstenhaber bracket with E1I1, then you increase the power of F until you are arriving at Fi to the n, and Fi to the n agrees again then with this sum of epsilon I and epsilon I plus 1. And if M is even, then the story is a little more, yeah, I wanted to say more ugly, maybe more complicated simply, because there these elements will belong all to one big indecomposable module, because so to say, one cannot separate them vertex by vertex anymore, but due to M being even, they kind of, yeah, overlap, and we find that all of them together live in the same indecomposable module. And a similar picture that I'm not going to give in detail because things get really quite messy. This is that the HH1 module structure on the nth Hochschild cohomology roughly looks very similar again. So we have one big indecomposable module that is generated over one element, and then everything that you can obtain from that element by taking the bracket with our E1JS. And maybe keep in mind that the degree derivations won't add anything because they act diagonally anyway, so you don't get anything new, anything new from these degree derivations. And apart from this one big indecomposable module, there will be just lots of one-dimensional modules. So everything else decomposes into just one-dimensional modules. So yeah, a quite interesting structure that we find this one big guy in each cohomological degree. And somehow, indeed, one can kind of see this. So Snellsche and Taillefer give the dimensions, and well, there's always this one, like quite different dimensions in each degree, but always greater than 1 plus m times n minus 1. And everything else is kind of behaving in a more, like, yeah, you know, it varies quite a bit. And all these other modules are just one-dimensional, so not very interesting from the module structure perspective. Now, you might wonder, where did the gradings really go? Because now I was just spending 10 minutes telling you what the structure was that we obtained, but not so much on how we obtained the structure. And this is what I would like to emphasize now. So the computational tricks that we used was to first observe that we can really easily determine the Gerstenhaber bracket with our degree derivations. So this is really a big recommendation to just start with any kind of degree derivations that you can get, because this will allow you to decompose Hochschild cohomology into the graded homogeneous components. And in our case, these summons were of really like very small dimension. So there was not so much living in each homogeneous component. And this enabled us to continue from there with 2 other observations. One, very simple, is just that by the Jacobi identity, the degree of such a bracket of 2 elements will evaluate to just being the sum of the degrees of these two elements. Now speaking again of internal degrees here, not to confuse with the cohomological degree, of course. And so from this, we know that either we have a new eigenvector, or this bracket here must be 0. And so either we are in the situation that we already computed everything, but because it's 0, or we just have to check again just a very small linear combination, because now that we know in which degree the Gerstenhaber bracket has to live, we just need to check the corresponding homogeneous component for some general linear combination, and then check whether we can compute the coefficients in this very small linear combination. This is also very convenient. And last but not least, we were making heavy use of the Poisson identity, and we typically applied it to expressions of the form. So we wanted to compute the Gerstenhaber bracket again of 2 elements x and y, and we just multiplied one of them with one of our degree derivations. And then by the Poisson identity and from knowing the cup products, we could try to hit as many zeros as possible from the multiplication table of the cup product. And then again, use the fact that everything here behaves well with the grading, so we just need to scan very small eigenspaces for the possible linear combinations that can constitute in the end such a Gerstenhaber bracket. And in fact, by using all of this, we heavily depended again on Mariano's method, because here we were allowed to just work with this much more explicit minimal projective resolution that Snusher and Taillefer gave, and for which they had already provided all the spaces and cup product material, so that we had a quite easy time actually going through this once everything unraveled itself, so to say. Now, of course, if we had known this recipe already in advance, everything would have been even easier, because we would have known what to search for already from the beginning. In the very beginning, we were kind of just standing in front of these quite messy looking bases, and those for Hochschild cohomology are of course much worse. I mean, they have rather high dimensions sometimes, and so we were really doing lots and lots of computations to see which of the Gerstenhaber brackets we can evaluate. And yeah, having gradings at hand is really very, very helpful. So we were really, after we realized in the very end only actually of the project that everything that we did could be organized very nicely with the gradings, I think, yeah, we found so both aspects quite nice, both the computational aspects that were so helpful, and that we just discovered, so to say, brute force, not knowing somehow these recipes at hand. And on the other hand, the gradings gave this very nice structure for our Lie algebra to have these root spaces and the central character, so to say, with respect to these two special elements that correspond to degree derivations. So this is really, in the Lie algebra world, behaving very much like Cartan subalgebras and center and yeah, being able to first of all make the problem smaller by computing central characters and see which parts have different central character, and then being able to organize the modules internally with respect to weight spaces for some commutative subalgebra, and then the remainder of the computations becomes really small. So this was yeah, what I wanted to tell you. So far you didn't ask anything. I hope that you're still here and the internet did not break down. But yeah, let me thank you for your attention, and yeah, I'm happy for any questions.
Okay, thank you very much for that very illustrated talk. Any questions or comments?
I have some questions or some comments. When we started, you said that the gradient derivations are more or less diagonalizable. And I want to say a diagonalizable derivation is the same thing as a grading over the group of the additive group of the field. Is the same thing. One can go from one or another. So a gradient derivation is the same thing as a diagonalizable derivation with eigenvalues in the integers. They are the same thing. That's one observation. Another one that I have together with some other people, with Daniel Farkas and Green and Daniel Farkas and Green. We did one thing that was that in characteristic 0 there is there is nothing. I mean, the notion we define is valid for every derivation, but in characteristic P is something different. We define integrable derivation is a derivation such that you can define automorphism ring between the formal power series of the algebra you start. We don't require the algebra to be basic. On automorphism, you take the formal power series, and there is an automorphism that fix A. So you start with A, then you take the automorphism period of A, and then your derivation is called integral if there is an automorphism where when you apply f of x, you get A, you get x. No, you get x plus or I think you get 1 plus, I don't remember anymore, 1 plus f of x, plus, and this f1 of x is a derivation, and then you do f2, f3, and so on. So if you can compute and the sequence of derivation, you say the derivation is integral. The integral derivation also forms a Lie subalgebra and is invariant for the set of it's invariant for Morita equivalence, and the diagonalizable derivations and the inner derivations is also integral. So we have in characteristic 0, you have another Lie algebra that's containing this one, that is the one of the integral derivation. I somehow have the impression that this is nice to be studied, and we are not able to prove that this guy is invariant under derived equivalence, but we proved that they are under Morita equivalence. So it's how you see one thing that I would like, I think I suggest, or I really would like to talk sometime more, to identify this integral derivation on what is the Lie structure here and how they are inside us. For characteristics, every derivation is integral. One can show that. So there is nothing new. But in characteristic P, there is something new there that perhaps to look at, and then suggesting to look at. And I would like to review what we did, because I was years ago and I forgot. Yeah. But I remember that one thing that I mean, it's just an exercise, that the integral derivations, that the diagonalizable derivations are exactly the same as the grading on the group of the field. That's easy. Yeah. But the other thing is harder. It's a little bit, for instance, to prove that those integral derivations are invariant over are invariant of Morita. We sweat a lot. And given examples of derivations that are not integral, we can do in characteristic 0, you can do the group ring, you can work in the group ring and give some examples. So that's that. Yeah. This is perhaps one way.
I really like this view. Also, your view on this notion of the diagonalizable derivations, and to see how they correspond to gradings, and that one can really so in this example that I was considering, of course, these two degree derivations were commuting, but I think it would be also very interesting to explore in very much the same way as Cartan subalgebras are conjugate, and you can have several of them, but they to really look at so to say families of simultaneously diagonalizable derivations as somehow one set of gradings, and as you say, so to generalize also away from classical Z gradings to the more general gradings is also something.
I think also what we are doing, what we did somehow is, I would say that is the infinitesimal automorphism of the algebra, because we can extend as I did in the beginning, but we can extend for the formal power series algebra. I remember that when I worked at that, then I stopped working on that, but I think I'd like to. Now you kind of convinced me that I should look at that 3 papers that we did another time, and perhaps something that you did. I think that you. The talk was very
nice. Yeah. So it, I would be definitely very happy because also I think this aspect that it is so not only of this theoretical beauty that you get this very nice structure inside first Hochschild cohomology, but the fact that you also get really quite big computational advantages from this, I think makes it really yeah, just a very nice object to study. And also just this idea of, well, looking at all gradings that you can equip the algebra with simultaneously, and not maybe just the one or two that you came across, but really going the other way around and looking at the first Hochschild cohomology and knowing that, well, there might be, of course, inner gradings, but the kind of remaining outer gradings are described inside the first Hochschild cohomology. I think this is very nice, and just giving also quite a lot of insight to gradings on algebras in the opposite way.
Yes, yes. Thank you. Thank you for the nice talk.
Thank you, then. Yeah, you maybe. So I stopped at the thank you page, but I should point out. I mean, I really enjoyed looking into your papers, yeah, I think so. It's definitely not a comprehensive list of literature, and I think more of it is, of course, in our paper. But it's, I think, this view on how important the gradings are, we only developed really somehow looking back at what we did, not so much at when we did it from the beginning, because this view, yeah, was kind of missing to us as we were having a starting point, rather this a tool set of a very explicit basis and very explicitly given cup products, and so we didn't start somehow from the question of how to make life easier at first, because we thought that it is already yeah, well, decently easy. Yeah, looking back at it, I think there's a lot of very interesting theoretical questions in there, and I think it would be great to explore a little bit more on how this theory and how this computational practice work together. Yeah, thanks a lot. Thank you.
Okay, any more questions? So I have a question, maybe for both of you, for Joanna and Eduardo. So if you have so if you have an inner grading, so it means that you have some element of degree 0, right? Does it have to be of degree 0 that will give you the so the element that produces the grading, does it have to be of degree 0? Not really, right?
Well, it will be kind of degree 0 with respect to itself, so to say. So you have to keep it, so there is no let me say universal notion of a degree around, but since the element commutes with itself, it is, well, it has degree 0, yes.
And so is it true that if you have an inner derivation, then you have an inner grading, then what you have is an OR extension where the automorphism is given by the identity. Ah, no, because I'm thinking of a different grade. Sorry, I was mixing a couple of ideas, but I'm having a bit of trouble organizing my head, but I'm thinking of if there is a way of taking a okay, so here's what I have in mind. If you have a grading that is not inner, you can sort of make it inner by force by adding an extra element and then doing the OR extension by this virtual element and using as a derivation the degree. do you know of a way to? Of course, this makes the Hochschild cohomology probably smaller, because then what was previously non-inner derivation has become inner. Do you know if there is a sort of inverse path of, if a certain derivation gives you a grading, but it is inner, then you sort of take it away? I'm trying to understand if there is a way to make this these gradings not go away when you produce the Hochschild cohomology. So they all appear as linearly independent in HH1.
But it means to also change the algebra, right? So you want to change the algebra. Yeah.
And the follow-up question is, if we know how to change the algebra, do we know what happens to the different Hochschild cohomology groups when you go from one to the other? But in order to make that question, I have to first ask if we know how to produce these algebras in the first place.
So I wouldn't know of anything that is really somehow meaningful. I mean, probably it's yeah. Probably one can switch to another algebra by some hands-on construction, but maybe it will be more or less just a coincidence than that it has the right the desired derivations around, right? Because I mean, adding another element or removing the element might also impact the rest, I suppose. So I don't know of any procedure, but maybe other people do. So I don't know. But I like the question. I think it would be really just very interesting to explore more about what role the different gradings really play, so both for the algebra and for the Hochschild cohomology. It's quite funny for me at first. So I mean, for me this was yeah, some. I'm not that acquainted with Hochschild cohomology. I just rather joined from the knee side, so to say, to this project group. And I think for me, having the algebras in mind, these inner gradings were somehow nicer, right? Because the algebra was already, like telling you what to use for the grading. Now in Hochschild cohomology, this is exactly what you lose. So yeah, nevertheless, these so to say, then outer gradings, even though it's maybe a bit sloppy to call them outer gradings because they arise from this quotient, and well, but you know what I mean. So these outer gradings, they are in the end really elements of this first Hochschild cohomology, non-vanishing elements, and they again somehow act then via this this inner bracket inside HH1, right? So you kind of switch perspective there, and so in the end you're very so in the beginning you try to avoid those derivations that come from taking the commutator bracket with algebra elements. And in the end, you take the Gerstenhaber bracket precisely with your degree derivations, and you get insights from that one. So, but it's just that you should not mix the commutator bracket in the algebra and the Gerstenhaber bracket, because both in a row will be 0.
Okay, so if there are not any more questions, we thank the speaker again, however we can.
Thank you.
And